All right. Hello, everyone. Thank you for joining today. We'll get started in just a moment here. All right. Hello, everyone. Thank you so much for joining us today for this webinar series. This is the first in a series of 4 webinars that are being co-hosted by the EarthScope-operated NSF National Geophysical Facility and CUAHSI. Before we kick things off and I hand things off to our speakers for today, we're going to give a brief overview of each of our organizations, CUAHSI and EarthScope. And just a reminder that we expect all involved with CUAHSI cyber seminars uphold the CUAHSI Code of Conduct and promote and maintain a professional, considerate, respectful virtual environment. So thank you for being a part of that. My name is Julia Masterman. My pronouns are she, her, and I'm the training coordinator for CUAHSI. CUAHSI is the Consortium of Universities for the Advancement of Hydrologic Science Incorporated. We're a nonprofit organization funded in part by the National Science Foundation. And our mission is to empower the water community and advance science through collaboration, infrastructure, and education. We seek to fulfill this mission in a number of ways, one of which being infrastructure and data systems. So CUAHSI sustains infrastructure to enable research and collaboration. We host a data repository for water science data called Hydroshare. By providing this support and infrastructure, CUAHSI can help researchers formulate and execute their data management plans, be effective data stewards, and meet the requirements of funding agencies and publishers. CUAHSI also provides educational opportunities and infrastructure for student support. These include workshops, a summer institute for graduate students, a webinar series, and events like this one, a virtual university, and more. Both our data infrastructure and educational opportunities are designed to enable collaboration and interdisciplinary work. Thank you so much for joining. And I encourage you to connect with us either through social media or by joining our mailing list and also checking out our YouTube channel. This webinar will be recorded and posted there later today. And with that, I will pass things off to Scott.
Hi, just also by way of introduction, the NSF National Geophysical Facility, which is operated by EarthScope Consortium, supports research in the geosciences using geophysical tools. My name is Scott Johnson. My colleague Emily Zawacki and I are Science Communication Associates at EarthScope. We were funded in 2025, this new NSF NGF, which provides instrumentation, data access, and educational resources for researchers, local governments, educators, and students, and other users. You can join our email list to stay up to date on upcoming events, job opportunities, service announcements, educational resources, and more. You can find us on social media as well. I know we'll be dropping all these links in the chat in a moment too. So this webinar series, this is the first of a 4-part series. So we hope that we'll join you for the remainder of the webinars in this series. If you're registered for this one, you're already registered for the others, so that's good. This series aims to highlight the work being done at the intersection of hydrology and geophysics and foster collaboration between geophysicists and hydrologists to broaden critical zone scientific communities. So today's webinar, the first of that series, is on current research in hydrogeodesy and hydroseismology. So huge thank you to our speakers today for taking the time to help us out with that. And before we get started, just a couple quick logistical things. So first, as Julia mentioned, this will be recorded and that will be posted on the CUAHSI YouTube channel. And secondly, we ask that you use the Q&A functionality in Zoom to submit questions to our speakers. So not the chat, but the Q&A button. Please feel free to add questions at any time, upvote those that are especially of interest to you. We'll do our best in the latter portion of this to get to as many of those questions as possible. Okay, so now to introduce our first speaker, Dr. Hilary Martens is an associate professor of geophysics at the University of Montana, and her research uses geodesy to better understand how Earth's surface deforms in response to processes like ocean tides, atmospheric pressure changes, and shifting water storage. So Hilary, please get us started.
Great. So thank you very much for the introduction. It's good to be here today. I appreciate the invitation. So let's go ahead and jump right in. So it's really great that all of you are here and that CUAHSI and EarthScope have jointly organized this series, because this is a really exciting space to be operating in right now at the intersection of hydrology and geophysics. And not only is it interesting, but we've also been seeing this tremendous growth in this field over the last few decades and impact. So this figure here is showing a number of publications as a function of time over the last few decades, and just this remarkable exponential growth trend advancing the water and climate sciences with geophysics. Now, much of that growth can be attributed to observational advances that we've seen, mostly satellite-based, across the spectrum. This is really focused on geodesy here, but from altimetry to INSAR, especially with the launch of NISAR last summer, there will be a lot of exciting advances taking place now with INSAR data. Gravimetry, so measuring changes in Earth's gravity field on time scales of months to years, is having strong signals from hydrology. And many of you may have heard of the GRACE missions, which are gravimetry and contribute significantly to that. What we're going to focus on today is this GNSS component, which stands for Global Navigation Satellite Systems. It's like the GPS that you have in your phone or in your car, but the instruments look a little bit different. So they look like this when we do the science for Earth deformation and water storage. This is an EarthScope instrument, actually, a GNSS station in California. And you can see they're typically anchored into the bedrock like this one. So when they're anchored into the bedrock, they move up and down and side to side as the surface of the Earth shifts around. And one of the reasons that the surface of the Earth shifts around is because of the movement of water and the weight of that water. For example, the snowpack that we get in the mountains, this is a heavy weight that applies pressure to the surface of the Earth, pushes it downward depending on properties of the Earth, how rigid it is. And then when the water melts and runs off, now the water has moved away and the surface of the Earth can rebound back upward. So that's what we see manifested in GNSS time series, just like this one. The blue dots are daily position estimates of a station just like this. And this is a time series over 8 years. Vertical displacement, the scale here is a few centimeters. And so we can see this really prominent seasonal signal here, where in this case, during the winter and spring months, there's a lot of downward displacement from the loading of heavy snow and groundwater. And then in the late spring and summer, the water runs off, it evaporates, and the surface of the Earth rises back upward now that that pressure has been removed. So we can take GNSS time series just like this one, how the surface of the Earth is deforming under the weight of water. And along with some information about Earth structure, how rigid or squishy it is, essentially, we can use that to quantify changes in total water storage. So this is an example using EarthScope Network of the Americas, GNSS stations here, turning that data into an estimate of how much water must have been gained on average each season to explain this data. And we find this is a really nice study by Donald Argus and others that in the mountain regions of California, example, up to like 3/4 of a meter of equivalent water thickness is gained on average each year. Now, I do want to highlight, because I believe we have many hydrologists here today, how this fits into the water balance. So geodesy really complements hydrology and meteorology, and one of the ways that it does that is by constraining this delta S term here, or changes in total storage, without the need to bookkeep these individual fluxes here. So normally this water balance is computed as water input, precipitation, minus water outputs from evapotranspiration and discharge. So normally that's how changes in storage would be computed, but geodesy provides an independent constraint on this delta S term. And we can use this or apply this in many different ways. So I'll just briefly highlight at a very high level some of the applications that we can apply this technique to. So we already spoke a bit about the seasonal water changes and quantifying those. But similarly, GNSS can be also used to track extreme weather, such as atmospheric rivers. So this is a atmospheric river is a narrow channel of concentrated water vapor transport in the atmosphere. This is one of the primary sources of water for the Western US. So GNSS provides us with a tool to be able to quantify how much water is gained from storms like these. And this was an experiment that we did, or a study that we conducted a couple of years ago, when there was a really strong sequence of atmospheric rivers that hit the west coast of the US between late 2022 and early 2023. On the left, we're seeing these are all the GNSS stations and the displacement that was measured over that 6-month period. You can see that many of them moved downward by about a centimeter or two. And then we can turn that into an estimate of how much water must have been gained to explain that downward deformation. And parts of the Sierra Nevada really got dumped on that year with up to about a meter or more of equivalent water thickness. GNSS data similarly can also provide insights into hydrological drought. This is a special drought metric based on total water storage changes rather than, say, just precipitation deficits. So it gives a more holistic picture of water storage and drought conditions. GNSS data also provide insights into aquifer and groundwater storage, which is really interesting because sort of traditional hydrologic methods, it can be challenging to sample groundwater from, for example, well data, which are point measurements, difficult to deploy sometimes and maintain, and there can be large lateral variations in storage. So GNSS provides insights more regionally into storage conditions, and there have been some really nice studies, a few of which are highlighted here, looking into groundwater and aquifer storage recently, such as in the Central Valley of California. GNSS data also provide insights into watershed behavior. So again, GNSS can put independent constraints on this change in storage term, and that can be related to stream discharge and sort of expected stream flow. And these signatures on the right, I'm showing an example of a hysteresis curve for a watershed in Colorado. And each watershed has a little bit different signature of how the storage conditions throughout the year are related to stream discharge. And that can be a function of many variables, the lithology, topography, the vegetation, the climatology, whether it's rain or snow dominated and things like this. So this can be used to forecast stream flow. And also, I just want to mention that, so we've been talking about geodesy, but seismology also provides insights into subsurface water storage. And this is a study from last year. Dr. Mao actually is going to be presenting as part of this series in a few weeks. So this is a preview of coming attractions, and I hope you'll tune in for that as well. And in particular, I guess seismology is complementary to geodesy because it provides enhanced resolution of water storage at depth. So yes, she will speak more about that, I'm sure. Okay, so looking ahead, I think something that is really exciting, and we're going to see more of it, and it's going to help to advance the field even further, is enhanced interdisciplinary integration. So, of course, the geodesy with the hydrology, meteorology, integrating more seismology. But another piece of this to highlight would be resource management. And there's already some work being done in this space, but I think a lot more sort of meaningful work can be done here, and there's a lot more to do. One example of this would be hydrogeophysical forecasting to help inform artificial reservoir operations. So this is highlighting an example from California. They have an extensive network of reservoirs there and that provide water to millions of people in agriculture. And because of Geodesy's ability to understand total storage conditions and how the watershed might respond, they can provide information to decision makers about how much water to retain in reservoirs to hopefully mitigate the risk for drought in the future, but also not retain so much as to pose a risk for flooding or infrastructure damage in the event that a large precipitation event like an atmospheric river were to come through and inundate the infrastructure. So it's really this balancing act, and geophysics certainly has a role to play here, and that role can certainly grow and advance with time. So we just have a couple minutes left here. What I wanted to conclude with is just to highlight an experiment that our team ran over the last several years. And to our knowledge, this is one of the first, if not the first, maybe one of the first, purpose-built networks experiments for hydrogeodesy, specifically for that application. We have a couple photos here from the field. A lot of students were involved. One of our GNSS stations is shown here. Here's the antenna. And then one thing we did was co-locate GNSS stations with weather stations. So an example of one of the weather stations is shown here. We had climate data, snow data, a soil moisture probe as well. And here's what the network looks like. This was at the border of Montana and Idaho that we had these stations deployed. Many of them, again, co-located GNSS with weather stations and in a pretty dense array. So here's the spatial scale here. EarthScope GNSS stations are shown by the pink dots, so it also sort of filled a gap in this region for monitoring geodetically the surface deformation. There was stream gauge data that we had supplemented with Forest Service and USGS data. And yeah, so again, specifically looking at water storage changes, quantifying those in a high mountain watershed. Okay, and one of the motivations here, this is looking at time scale versus spatial scale for some different geodetic techniques and sort of just broad characteristic scales for these. You can see GNSS is here in the orangish green box. And one of our motivations was to sort of push the boundary on this left-hand side, the spatial scale of GNSS, which has a lot to do with the density of the stations, and to some extent also the lateral heterogeneities in the load itself. So doing this high resolution hydrogeodesy is why we deployed stations in such a dense array. Okay, and this is the last one. So I won't go into detail on the data, but one of the reasons I wanted to highlight this is because the data are publicly available, and the hydrologic data are archived with CUAHSI, and the GNSS data are archived with EarthScope. And both can be found here in Elisa White's paper from 2023, along with a description of the network itself, all the many learnings that we had through its deployment, including the sensors, the panels, the power systems, the GNSS antenna getting buried with snow and having teams try to dig them out so we don't lose too much data and have too many gaps. So I encourage you to check that out. If you're interested, this left QR code explains more about that network, including links to the data. And then there are some other resources that you can check out with the other QR codes here for further exploration. So I'll leave it there for now. Thanks for listening.
Thank you so much. All right, if you in the audience have any questions for Dr. Martens, please feel free to put them in the Q&A. We're going to hold those to the end, but while they're fresh, please feel free to put them in the Q&A. And with that, I would like to introduce Dr. Holbrook. Dr. Holbrook is a professor of geophysics at Virginia Tech. He uses geophysical techniques to examine Earth processes and specifically focuses on critical zone geophysics. He serves as the lead PI of the bedrock cluster of the Critical Zone Network, which works to unravel the feedbacks connecting bedrock geology to critical zone structure and function. We're very grateful that you're taking the time to join us today. And without further ado, please take it away.
Okay, thanks, Julia, and thanks to both CUAHSI and EarthScope for the invitation to speak on hydroseismology. And I want to thank all my students who, for the stuff that I'm going to show you that's coming out of my lab, who actually did the work. But hydroseismology is a big topic, and I think what most people will think of when they think of hydroseismology, in just a general sense, it's the use of seismic waves to detect the presence of movement of subsurface water. But most people will probably think of passive source approaches as hydroseismology. There are also active source approaches to this, which I would just call critical zone seismology, which is what I do. I didn't want to just give a talk about what I do here on a topic as broad as hydroseismology. So I'm going to, what I'm going to do is not do justice to either of these two approaches, but try to hit some highlights on both. So I'll work from the passive to the active, finish up with some of the stuff that my group is doing, but hopefully in the process, give everybody an overview of sensu lato, what's happening in applications of seismology to hydrology. And spoiler alert, at the end, I'll make a pitch for trying to combine these two approaches more often than they are. In a general sense, passive source methods are listening to the sounds that are just propagating through the earth. Whereas active source methods are creating their own sounds by swinging a sledgehammer or firing a shotgun or using vibroseis or whatever. Passive source methods tend to record on either three-component seismometers, maybe broadband seismometers, or increasingly on fiber optic cables, distributed acoustic sensing or DAS. Whereas active source tend to be portable geophones or nodes. Talk about those in a few minutes. Passive source tend to be longer term deployments, months to years, whereas active source short term, days. Passive source tend to cover larger areas and deeper depths, lower seismic frequencies. Active source, higher frequencies, smaller areas, think catchment size, not watershed size, and shallower depths. Passive source methods mostly in the literature provide time-lapse information, most often delta V over V, changes in velocity over time that reflect changes in water table depth, but they don't really give a lot of detail about subsurface structure. That's changing a little bit, but in general, that's a true statement. Whereas active source methods are really meant to provide that structure and to give a porosity map of the subsurface, but they aren't really used much for time-lapse information because it's pretty labor intensive. Okay, generally passive source hydroseismology uses ambient noise, which are sounds propagating through the earth. If you have two stations and they're recording this noisy seismogram, just whatever is propagating, just listening. If you cross-correlate those and stack and filter, what emerges is the Green's function, or basically the impulse response if you had a source at A and a receiver at B or vice versa. And what you tend to get out of this is a surface wave, a Rayleigh wave usually, but this would be the signal propagating from A to B, this from B to A. And it's giving you a sense of how long it takes a surface wave to travel from point A to point B. And these can be used to look for very, very small changes in travel time between them. They're typically deployed at over large areas. I don't want to go into any detail on either of these, are just example maps. The point here is this is the LA basin at the scale here, 40 nautical miles, so something like 75 kilometers. Over here, 10 kilometers, 20 kilometers. So the scale of the passive source hydroseismology tends to be tens to hundreds of kilometers and can be applied with just a few stations, really with just two, or with many stations if you want more detail. Increasingly, there's a lot of work being done with distributed acoustic sensing. This uses an interrogator in a fiber optic cable that's underground, usually a dark cable, so one that was formerly in use for communication but is no longer in use, and gets reflected laser light coming back from imperfections all along the fiber optic cable, and from this can reconstruct seismograms that look like this. This is from Tribaldos and Ahu Franklin a few years back. And what you mostly see here, I think there's a little bit of P wave energy up here, but mostly because the fibers are horizontal and they're recording strain in the direction of the fiber, they're mostly getting horizontal components, so mostly shear waves. But it's great because it can just be interrogated passively over months or years, and you can see very, very subtle changes in arrival times, like right here. This would be a shear or a surface wave that's getting a sudden delay. So something happened here, probably something hydrological, and then that change in travel time is just related to a change in velocity by simple proportionality. The negative sign is because if travel time increases, that means that the velocity is decreasing. The physical mechanism behind this is thought to be changes in water table level. Because these methods generally give shear velocity, not P velocity, what they're really sensing is a change in pore pressure as the water table rises. That imposes a higher degree of pore pressure at depth, and the pore pressure kind of pushes the grains apart, acts against confining pressure, and velocity goes down. So when the water table rises, seismic velocity goes down, and vice versa. So what you tend to see are time graphs versus time of changes in velocity. This is in percent over here, and then compared to some kind of a hydrological measurement, like in this case, river stage or precipitation or groundwater levels in a well. Here's an example from Mao et al., which shows really high sensitivity. If you look at the scale over here, this is delta V over V in the top left, and these are a few hundredths of a percent variation. So very, very slight changes in the phase of seismic arrivals. And these can be correlated really nicely to hydraulic head in a nearby well and applied over large areas. So these are the typical products from passive source hydroseismology, time-lapse graphs of delta V over V, often compared to some kind of a hydrological data set, and then spatial maps. It's a growing field, lots of successes. This is from a summary paper by Marine Denol and others. But none of these studies, and I've looked, none of them show structure. So where the changes are happening at depth. And depending on what your science is, for many hydrological problems, structure matters. Here's an example from a paper by Hong Chen and others a few years back where they took now active source seismic measurements in a small catchment. So this scale here, these are 50-meter ticks. So the entire thing is 150, 200 meters long. So catchment scale. They gridded these velocity models, which tell us what the thickness of the regolith, fractured bedrock, intact bedrock is across this. And then they modeled that data with 4 different models of increasing complexity that took more and more of the information in from the geophysics. And what they found was to really match the hydrograph better, the geophysics-informed structure is a big help. This is work that's not yet published, but I think is just about to be published, but it was shown at AGU, and Zhuye Kang graciously sent this to me. This is now airborne. It's not seismic. It's airborne EM data from a watershed in Colorado. Look at the scale bar here. This is now like 5-6 kilometers across. So watershed scale. They used electrical resistivity from airborne geophysics, and again, tried a few different hydrological models of increasing complexity, taking in the third model, the subsurface information from the AEM. In contrast to the Chen et al. Work, they did not see a big difference in the discharge, so in matching the hydrograph, suggesting some kind of equifinality at the scale of a watershed, but a big difference, and this was fascinating, in the chlorine concentration. So if you're interested in CQ patterns and how solutes are moving through the watershed, the subsurface information makes a really big difference. All right, a couple minutes now for active source hydroseismology. And the main point I want to get across here is this is a very rapidly changing field. This is photos of some of the folks in my group in the Sequoia Grove. We're using nodes. This is one of the game changers that's happening right now is autonomous nodes, accelerometer nodes. It's completely changed the way that we work. We bought a couple thousand of them. This is one of our undergrads, Bella. She's carrying 100 on her back. 2,000 of them and all the necessary accoutrements fit in the back of a Suburban. So it's a game changer for how you can deploy things. The other thing that is a game changer is application, broader application of full waveform inversion for critical zone science. This is from a paper by my PhD student, Ben Eppinger, a couple years ago. And the point here is that almost everything that's been done in critical zone science to date is a travel time tomogram like this, where the first arrivals are used. But increasingly now we're seeing the application of full waveform inversion, which gives a lot more detail on for example, here, the shape of the bedrock. Does it matter? Well, I think it does. So I've started a collaboration with Hong Chen, now at the University of Iowa, where he took that full waveform result and the shape of the fractured bedrock and made a hydrological model out of it, and then saw that, in fact, at this scale, at this sort of catchment scale again, the hydrograph changes. The runoff is less flashy, more delayed, which suggests a kind of fill and spill model at the top of the fractured bedrock, which was, in fact, I think, anticipated by Brady Flincham a few years back in his Vados Zone journal paper, where he used NMR data to infer the presence of water that is ponding at the top. This is exactly the same location, ponding at the top of the fractured bedrock, and that obviously is going to have an impact on the hydrology at this scale. So whether you care about this depends on the problem that you're working on. In the 30 seconds I have left, I'm going to just give you a brief look at some work we've done in the sequoias, and this ties to eco-hydrology. And really the big question here is, how do the sequoias support themselves? Where do they get their water? Unlike the coastal redwoods, they don't have a big subsidy from atmospheric fog, from atmospheric water. So we've been doing some work up here. This is, again, Ben Eppinger's work. He's going to be defending his PhD in a couple of weeks. VP-VS from full waveform inversion, you get both VP and VS. That enables you to do rock physics that can give you porosity models and saturation models in the subsurface. By the way, these trees are not schematic. This is a handheld LiDAR image of the trees at the site. The tallest ones are sequoias. And here, if you multiply porosity by saturation, you can get water content. So this is a water content map at depth. And so now we can see where is the water that the sequoias might be getting. And the bottom line is there's not a lot in the upper 10 meters. The standard line on how deep sequoia roots go is 1 meter. We don't think that can be true given this. If you look at these closely, you can imagine that you can see this sequoia drawing water from down here, these two sequoias drawing water from down here, rock moisture from the fractured bedrock. So the roots have to go either much deeper than previously thought or very far. I'll finish with this. I've sort of talked about two different kinds of seismology applied to hydrology. I would love to see combined surveys in the future. This could be really exciting to leverage the strengths of both methods to do the time lapse, but to put the time lapse changes in the context of the structure that's there. So with that, I'll end. Thank you.
All right, wonderful. Well, thank you so much, Steve, and also thank you to Hilary for these wonderful presentations. We're going to move into our discussion and Q&A portion now. So again, please put any questions that you have in the Q&A. It can either be directed to a specific speaker or just kind of more broadly in terms of combined hydrogeodesy and hydroseismology. We're going to start off with a little bit of a larger scale discussion. So I thought it'd be interesting to ask Hilary and Steve about spatial scales, because we saw a number of maps, some of which covered kind of the entire Western United States, and then other maps were kind of showing catchment scale studies. So if Hilary and Steve can talk about how large or small could you expand or shrink a hydrogeodesy or hydroseismology study?
I can start. So it's a really great question, and this is like a huge topic that we're interested in, right? So pushing the boundaries kind of on both sides, but especially towards the small scale, because we understand that that's of significant interest for hydrology, is to understand water storage changes at the catchment scale. And really from a geodetic perspective, so there are some limitations in terms of the satellite data, such as from the GRACE satellites, for example, that the way those measurements are done, they're more sampling a broader scale of water changes, regional to global. GNSS, it's really dependent a lot on the spacing between the stations. So in some way that can be controlled. If you have unlimited resources, you can really do a lot there. INSAR is another one though that can really get fine spatial scale deformation, but more limited in terms of temporal resolution. So there are some trade-offs, but I think again, back to interdisciplinary aspects to this and integration of different data sets that are independent of each other and looking at the Earth system in different ways, that those boundaries on the scales can be pushed, including to the smaller catchment scales.
Yeah, and I would say for the seismic side, well, the scale issue is a really important one, and it's a big one. I'm not a hydrologist, but I've spent enough time talking to enough hydrologists to know that scale matters in hydrology, and it's kind of a vexing problem there when you measure hydraulic conductivity at, in a soil column and then try to scale it up to a catchment, you might not get the answer. So because there are things happening outside the scale of your soil column experiment, and that goes all the way up. There's this concept of equifinality in hydrology that you can sort of get the right answer for the wrong reasons or for not really knowing all the reasons, because things kind of get averaged out. I think that the example from the group at Colorado School of Mines that I showed shows that the more detail you look at, so that where they had to understand the solute flux through the watershed, they needed more information, and that says something about transit times and how long water is staying in contact with certain parts of the subsurface, and therefore how long it can actually leach solutes out of the rock and the soil. So in terms of scale is a big issue. In terms of what seismology can do, your main limitations are frequencies and what frequencies propagate through the earth at different scales. And in general, the larger the scale that you go to, the lower the frequencies you can record, and the lower your resolution, deeper the depth is going to be. There's not a limit at the small scale. I mean, we've done some stuff with our nodes where we put the nodes out at 10 centimeter spacing, and swing a sledgehammer at half a meter spacing to try to look at soil structure. And I've seen some stuff in the passive source literature as well that's starting to do sort of laboratory scale experiments and looking at surface waves there. So both methods can be scaled up or down, and I think that really the choices that you make just depend on what your science questions are.
Yeah, fascinating to hear about. I know, Hilary, you mentioned you were conducting an experiment in the Northern Rockies. That was kind of one of the really first focused hydrogeodesy catchment scale. And Steve, you mentioned another focused studies and also distributed acoustic sensing. So I'm wondering if you can kind of comment on where you envision future practical field applications going, or in terms of new instrumentation that could be used or new ways to use existing instrumentation to answer these different questions.
I was going to say, go ahead, Hilary. Well, I think that I'm less familiar with how instrumentation is changing on the passive source side. I'm not an expert. I'm familiar with those techniques. I'm not an expert in that realm, and I certainly don't want to pretend to be one. But in my recent experience, as I said in the talk, that the game-changing instrumentation change has been accelerometer nodes. They're light, they're small, they can record for a month or two on one battery charge. So they can record ambient noise, from half a hertz to 200 hertz. They're great for active source, and I think they probably could see a lot of use in passive source. They can be deployed, they're accelerometers, so they can be deployed at any orientation, so you can get 3 components out of them. So I'd be really interested to see folks in the passive source world also start to use those more and see what kinds of things we could do jointly.
Maybe just to add to that, because I agree from the seismology perspective, the nodal seismometers have been transformative, and in terms of dense field operations and also DAS. From the geodetic perspective, of course, a lot of the data is satellite based, but more missions like NICE are going to also transform our understanding of the Earth system and specifically the hydrosphere. It'd be great to see more advances in terms of low-cost GNSS instrumentation and sort of innovation in how those can be deployed. It would also, one of the learnings from the network that we deployed, it would be really great to have some innovation in station design that would allow the monuments to be taller but still stable. And that's a really difficult challenge, but to get the antenna above higher snowpack, but still keep it a stable monumentation. So those aren't easy things to solve, but could, with hydrogeodesy in mind, as opposed to sort of more tectonic applications, it could be neat to sort of push in that direction.
Right, and then I'll just pose one last broader scale question before we move into our Q&A, because we have a lot of great questions from attendees. In your experience in this kind of intersection of collaborative research, have you encountered or noticed differences in how a classical hydrologist might think about something, or the questions that they might be answering versus somebody who comes from more of a standard geophysical background?
Yes. Yes, I think definitely in thinking about the physics of the hydrologic systems, different reservoirs, hydrologic processes, how water moves through the ground. Lots of interesting questions and ideas there that I had never really considered before, coming from the geophysics perspective. Another thing that comes to mind is one that we already spoke about, which is scale. So a lot of traditional hydrology is sort of point scale, measuring precipitation at a point, or snowpack at a point, or well date at a point. And geophysics in that sense brings a very different perspective, because the loading, for example, it deforms the Earth. Even if you're measuring it at a point with a GNSS station, that's sensitive to deformation across a much broader scale. So a part of it for me with interacting across these disciplinary boundaries, I learned so much because we came from different perspectives of scale as well, in addition to the physics. So, yeah.
I would just add to that I've had some experience working across disciplines in other realms than just critical zone science and hydrology or hydroseismology. Sometimes there is a tendency, I've certainly been guilty of this, when you're coming from your discipline to, for a seismologist, say, to realize, oh, I can see this signal and it connects to this process. How cool is that? This is so cool. And write papers about how cool that is, that we can see this stuff. And it's really important to talk to the domain experts. If you're wandering into hydrology and you think your seismology is relevant, make sure that it's relevant to the hydrologists, right? It might be interesting that when it rains, the water table goes up and you can see it, but it might not be interesting, right? It might be kind of, yeah, that's what happens when it rains. And so working across those boundaries and really trying to understand what are the problems that hydrologists are trying to solve. And they could be anything from drought and aquifer, behavior to the fine scale. How does water get through soil, and does it turn left at the soil saprolite boundary or not? And everything in between. And you really have to understand what the domain experts need.
Maybe just to build on that briefly, because I really love what Steve is saying, and I think that's so important. And has, in terms of interpretation, been really important to have those different perspectives and expertise at the table. And then in addition to that, how can it be applied to benefit also society, because hydrology has so much impact across different sectors. So thinking about what are the needs of water managers and what are the needs of decision makers around the reservoir operations or drought management or things like that. So that has also been a very cool aspect to this and important to have the broad expertise at the table.
Thank you for that perspective. We'll hand it over to Julia, who will go through some of the audience Q&As.
Yeah, thanks so much. We've got plenty of great questions coming in via the Q&A. Audience members, if you want to upvote any questions that are especially of interest, that is helpful, or feel free to keep them coming. We'll get to as many as we can. And just a reminder, this is the first in a series of 4 webinars. So if we can't get to everything today, hopefully we'll be able to answer many more questions as the series continues. But first off, this is a combination of a number of questions that came in for you, Hilary. How do you account for things like tropospheric error versus a deformation signal, or water storage variations versus a tectonic process?
Yes, this is a really good question because, of course, geodetic data, especially GNSS data, has everything in it. So the satellite signal propagates through the troposphere. We have to model and remove that in order to get an estimate of position. That position data contains everything that affects the deformation of the surface, which includes tectonic deformation, GIA, volcanic, and water storage. So there's a lot to unpack there. I'll try to be brief. One thing, so we did a study a few years ago looking really specifically at the tropospheric delay. Something that benefits us for more accurate positioning is to use high resolution tropospheric mapping functions, high resolution in time. So there are ways that can model this more precisely. Atmospheric pressure loading is also something that contributes to the time series. And this is something that can also be modeled and removed. And fortunately, for the most part, atmospheric pressure loading occurs at different time scales than hydrologic loading. So that's one way to sort of differentiate as well, or that they're not so overlapping in the frequency space. But they are actually similar magnitudes. So a lot of the variation that you see in GNSS time series is not actually noise, but it's things like atmospheric pressure loading. That actually complicates the ability to use GNSS data, for example, to track water storage changes at the storm scale, like really when a big precipitation event is happening. But this is also kind of an exciting space to be working in because there are some sort of approaches that can be applied to analyze the data and get some insights out of that. In terms of tectonic, one thing that's quite common is, like in the studies in California, is to neglect the horizontal component of deformation and just look at the vertical in terms of the GNSS data. So most of the tectonic deformation is in the horizontal components. Again, it comes down to time scale too, that we can do some differentiation because tectonic deformation tends to be on the longer term. That said, it overlaps with multi-year drought signals. So this is difficult to distinguish between them. And I'll just end by saying that one thing that helps is to use multiple independent data sets as much as possible, and that can help to mitigate some of the non-uniqueness.
Great. Thanks so much.
Mm-hmm.
All right, this next question I think is mostly pointed to you, Steve, but feel free to correct me if that doesn't make sense. Firstly, they say thank you for these beautiful and insightful presentations. I would like to know if these 2 methods are applicable in urban areas. Are there any financial advantage to certain geophysical approaches compared to other techniques?
Yeah, I think this is probably one that both of us could answer because it's probably relevant to both. Certainly for working in urban areas, it's a noisier environment, but that can be good for ambient noise studies. It's generally bad for active source studies, but there are definitely examples of successful active source and passive source studies in urban areas. So there's no, there are going to be limitations on where you can put things, and people have done creative things, dragging geophone streamers along the street in the middle of the night, and setting off small sources or something like that, but it can be done.
Great, thanks. All right, zooming out a bit. This is kind of a broader question. What do hydroseismology opportunities look like in terms of graduate programs? As an undergrad aiming for grad school, the programs that combine both a PhD or a master's seem limited in this field.
My advice here, as after a long career in in academia and 8 years as a department head, and all the academia is changing right now, and these are challenging times. I'll give you the advice I would give anybody applying for grad school in any field. Communicate with the people in the US. Generally, you're not just applying to a program, you're applying to work with a mentor. And so you want to be in communication with that mentor and find out if they're taking students next year, because that's usually funding dependent. And these are weird times for funding. And because they're weird times, I'll give this piece of advice more emphatically than I have in the past. You probably want to apply to a lot of programs. I think that right now, because of the uncertainties in funding, I'm seeing fewer offers going out in a lot of departments because there's so much uncertainty. So just really try to apply to a bunch of programs, but communication with mentors. So read the literature. Who's doing the cool stuff? What are the cool papers? The stuff that you want to do, and reach out to those people over email and ask them if they're taking students or not. Is the best way.
Yeah, great advice. And I'll also take this opportunity to plug the fourth webinar in this series, where we'll have more of a career focus panel discussion. And so much more to come on how to pursue this type of work more broadly as a researcher or as a student into the future. Okay, a data question. Is GNSS an open source data for some part or for all of the US? And what is the coverage of GNSS data? What does that look like for outside of the US?
Yes, so that's a good question, and can highlight EarthScope here because yes, there is a lot of publicly available data, GNSS data for the Western US in particular, also Alaska. It's called the Network of the Americas, or NODA, and these data are archived with EarthScope. That said, that's the raw data, which could then be processed if you would like to process it in a customized way on your own. But there are several analysis centers that have already processed the data into position estimates. So you can also download the time series directly of positions. That's also a great way to go. Outside of the US, so if there are disparities in terms of network coverage globally, absolutely. Europe has pretty good coverage, as one might expect. But certainly some parts of the world are less well instrumented. But maybe, so there are opportunities there. I think, again, thinking towards innovations in lowering the cost of ground sensors and things can help with this in the future. But as far as publicly available data goes, the US and in particular the Western US and Alaska are great places to start.
Great, thanks. Okay, we have three semi-specific but similar questions for you, Steve. Um, One asker is about to start a project to monitor aquifers in southern Portugal using seismic methods. Being a passive seismology person used to surface waves and seismic ambient noise, I would like to know what you'd suggest as active sources and how you go about broadly kind of choosing active sources.
Yeah, well, there's a lot of just, factors that go into the decision of what source you're going to use. So the first one is what's your depth of interest? So how far do you need your seismic energy to travel, which relates to how deep it samples. Um, the noise level where you're at. There might be permission or environmental issues. My group generally tends to work in mountain watersheds, and so a lot of national forests or national parks, and so we're generally swinging sledgehammers. You can stack by swinging multiple times, and that works up to a point. But if you need to get deeper than, say, 60 or 100 meters at the most, then you need something else. So then you need to, the next sort of level up would be some kind of a shotgun source, like a Betsy gun or a Buffalo gun. There you might not be able to permit that everywhere. I don't think that the national park would let us do that. And then beyond that, there are weight drop sources, vibrator sources that go larger and larger right up to industry scale. So access is a big one. It's very difficult to get any kind of mechanized source. If you need something big from a weight drop up to a vibrator, that can be very difficult to do on anything other than a golf course or a road. So all of those factors, depth of interest, frequencies that you need, size of source, and permissions and access are the things that would factor into that decision.
Thanks. And then another question, can flash floods or water flowing in a river waterfall generate seismic signals that can be used for either subsurface imaging or to study the flow itself?
Hmm. Um, I think so. I know for sure that so hydroseismology can be considered just sort of one part of a larger field that's usually called environmental seismology. And there are people who look at in that sort of passive source, listening to things that sounds that the earth is making. There's certainly a literature about looking at flash floods through the sound that tumbling boulders or rocks in the stream bed make. There's some really cool papers on that. I don't know about the water itself making a sound but probably. I don't see why not, but I'm not familiar enough with that literature to say.
Very neat. Um, all right. And Hilary, what is the usual lag time between an extreme precipitation or recharge event and the signal response that you might see?
Yeah, this is a great question. So actually, the response of the Earth at those timescales is virtually instantaneous. So this is an elastic response of the solid Earth that, as soon as the water is applying that weight to the surface, that the Earth is instantaneously responding to that pressure loading. Um, the In terms of lag time, then there's no lag time. This is an elastic response. That said, if you're sort of isolating responses of different reservoirs, like maybe the response of a deeper subsurface reservoir to water infiltration, then that's a bit of a different story. But GNSS and Geodesy are sensitive to the total vertical water column. So as soon as there's a mass change, the stations, even far away, hundreds of kilometers, will be reflecting that at the same time.
Thanks. Yeah, that's great. All right. I think this might maybe our last question. We're almost at time. So very quickly, can INSTAR produce similar results to GNSS, especially for areas in the world where there are almost none or very few GNSS stations? Can we depend on INSTAR? What are the limitations here?
Excellent question too. Yeah, especially with NISAR, it's a very timely question. And so, yes, this is one of the huge advantages of having satellite data from INSAR, is because of that global coverage, repeat passes that can image all parts of the world, regardless of capabilities for various reasons of deploying ground stations. So it overcomes the limitation of having to do that on the ground like we would have with GNSS. In terms of limitations, the satellite signals, again, have to propagate through cloud layers and things like this. They can be affected by snowpack on the ground, which can degrade the signal, for example. But the NISAR mission, it has, and I'm not an expert in this, but has a couple of different frequencies to mitigate some of those limitations. So I think there will be a lot of cool science with application to hydrology coming out of that for all different parts of the world, and even where GNSS can't reach. So, yeah.
Great. Well, thank you so much. This is really exciting science, and thank you for taking the time to speak with us today. Thank you also to everyone in the Q&A for your great questions and participation. We wish we could have gotten to all of them, but over 200 of you joined today, so thank you for taking the time. And we hope you'll join us in 2 weeks for the next webinar in the series, same time, 2 weeks from now. But thank you again, and have a great rest of your afternoon.